More physics. Yippee! Especially on incline planes. Oh my god. Why am I cold? Do I have the cold? I don't think I do. Anyway, a ball is released above an incline plane and it bounces elastically, so it doesn't lose any velocity. So, like, think about it like this, at this, at this. The time and distance between each collision. Okay, so remember what we could do? We could do the cool trick where we just rotate it. And give me a second. We can think about it like this. The ball has remember the two components of gravity now? G cosine we'll say theta and G no, it's the other way around. Sorry. Oh. Here we go. Yeah. So as the ball progresses down the plane, the time and distance between each collision will what? So we don't have a plane here. I mean, we don't have like an inclined plane, we just have a plane. We could just say that the inclined plane is really, really, really long, and we just say like the ball bounces infinitely at that point. So it's whatever. So the time between each collision is the same, right? It's constant velocity. It's constant gravity. Yeah, it's always g cosine theta. I don't see how it'd be different. Like it would be different if like it like sped up, but like yeah, I don't see how it'd be different. Gravity's a constant, so the time would have to remain the same. The distance between each collision will increase. It's A. So basically, how I got increased was because, like, think about it. So for the first one, the time for each between each collision bouncing up and down, up and down, up and down. We covered that in like the max like time in the video where we were like talking about like how do you find the time of the ball or something like that. Like we figured that out. That's always like T V sine theta over like G like cosine alpha. It's always that because it never loses any velocity. So it's always that. I hope that makes sense. Like if I threw this ball up and it went down, it'll always go up because it never loses any velocity because the collisions are elastic. If it did, like in a real life term, of course it would like go like this, but that's because of air resistance. We're ignoring air resistance. We usually ignore air resistance not because it's not useful. It's just like really annoying. Like a lot of calculus. You know what I'm saying? Just to simplify it. And the as a ball the distance it will increase, right? Because there's acceleration. If we think about what acceleration like physically means, right? Like if we had a zero acceleration, the ball will like it'll move equal times at equal distances. But if we start accelerating, like think about like a car, right? A car is just driving, it will move like let's just it's like cruising, zero acceleration, it's just like moving like velocity. But like if it starts speeding up, also known as accelerating, then it'll cover more distance in different times, in like less time. Cover the same difference in less time, basically what I'm saying. And that is fully dependent on this component. Yeah. How about I explain that well enough? Yeah. Alright, thanks for watching. Yeah.